Hello viewers, today in this part of the lecture we will continue to discuss combinational logic analysis and design, and the outline for today's discussion is as follows. We will start the discussion with half and full adder, then we will move on to subtractor, then the next discussion will be on 2 by 1 and 4 by 1 multiplexer. Then we will discuss the logic function from multiplexer. Then we will discuss 1 by 2 and 1 by 4 demultiplexer, and then we will discuss encoder and decoder, where we will take the example of 8 by 3 encoder and 3 by 8 decoder. Adder and subtractor. Now, in binary addition we usually follow the following rules, that is, when we add the binary numbers we have to follow the rules as shown, that is 0 plus 0 is equal to 0, 0 plus 1 is equal to 1, 1 plus 0 is equal to 1, 1 plus 1 is equal to 1 0, where 0 is the sum and 1 is the carry, and 1 plus 1 is equal to 1 1, and 1 is the sum and the other one is the carry. Similarly, there are rules for subtraction, and which are 0 minus 0 is equal to 0, 1 minus 0 is equal to 1, 1 minus 1 is equal to 0, and 1 0 minus 1 is equal to 1. So, let us first discuss the binary addition part, and in electronics the addition is done by half and full adder. So, what is an half adder? So, it is a logic circuit that adds 2 bits such that the sum is the combination of the two inputs in such a way that they make the output as the output from a XOR gate formed by the two inputs A and B, and the carry is the output obtained from an AND gate, where the inputs are the input of the half adder. So, here we have shown the symbol or the logic circuit for the half adder, and the corresponding truth table is beside the logic circuit. As you can see from the truth table, there are 4 columns, 2 are meant for the inputs A and B, and the other 2 are for sum and carry. So, here you can clearly see that this output that is mentioned in the sum column is exactly the same output one would get from XOR gate. Similarly, the output that is obtained and is shown in the carry column is exactly similar to the output that one would obtain from an AND gate. So, the sum satisfies the XOR gate condition and carry satisfies AND gate condition. Now, we will discuss about full adder. In half adder, we can use only 2 inputs to get the addition done, but if there are more than 2 inputs, then half adder will not be able to perform the task. So, in that case we will need full adder. So, what is a full adder? This is a logic circuit that adds 3 bit inputs, and the output of sum and carry satisfy the following expression, that is, sum is a combination of XOR gates. That is, if we are considering 3 inputs A, B and C, then sum is equal to A XOR operator B XOR operator C, and the carry can be written in the following way, that is, carry is equal to A dot B plus A dot C plus B dot C. And the logic circuit for full adder is also shown here. Here we have used 3 AND gates and 1 XOR gate, and finally one OR gate to obtain the carry. So, the sum is obtained from the XOR gate and the carry is obtained from the OR gate, and here we have used 3 inputs, but these gates can be cascaded to some higher number as well. Now, how would we sum the binary numbers? So, let us try to understand that. For that we will discuss binary adder. So, these are logic circuits that can add 2 binary numbers. For example, if we want to add 2 binary numbers A3, A2, A1, A0 and B3, B2, B1, B0, then the following can be done. So, here we have shown the logic circuit for the binary addition of 2 4-bit numbers. So, here we have used a combination of half adder and full adder to perform the task of sum of 2 4-bit binary numbers. So, here as you can see the LSB of the 2 numbers, that is A0 and B0, they enter into the half adder at the extreme right of the logic circuit, and we obtain a sum which is mentioned as S0 and a carry which is shown as C1, and the carry from this summation goes to the next adder circuit which is a full adder, and it will add up with the next 2 numbers, that is A1 and B1, and it will give a sum of S1 and a carry of C2. So, if you keep following the same method, then we will obtain the sum of the 2 4-bit binary number, and that is represented as C4, S3, S2, S1 and S0, and in this way we can perform the addition of binary number by using binary adder. Next, we will discuss 2's complement adder and subtractor circuit. So, here in this slide we have shown a logic circuit which can be used for both addition and subtraction. As you can see here, along with the input that is given to the full adder in terms of the bits of the binary number, we have another input which is called sub, and that is acting as another input which will control whether we will perform the summation or subtraction task. So, for addition, when sub is equal to 0, B bits pass through the controlled inverter without inversion. So, the full adder produces the sum of A plus B, where A represents the binary representation of a number and B represents binary representation of another number. The final carry here is not used because S3 represents the signed bit and S2 and S0 represents the magnitude bit. Now, during the subtraction, sub has to be equal to 1, and if it is equal to 1, then the inverter produces 1's complement. Now, further a high sub, that is if sub is equal to 1, then it adds 1 to the 1's complement, hence we get 2's complement of B, that is B prime. So, the output now will become S is equal to A plus B prime, which is in other word is equal to A minus B. So, the 2's complement is equivalent to a sign change, and hence the subtraction can be carried out using 2's complement. Multiplexer, or in short it is called MUX. So, these are combinational circuits which select one out of many input binary data. So, it is mainly a data selector. So, inside the multiplexer, there exists a dialer which decides which input to be fed to the output. Now, the logic for the dialer is decided by the select lines, and here in this slide we have represented a block diagram for a multiplexer where we have two select line S0 and S1. Now, how many select lines would be needed for a given mux can be calculated by using the following expression, that is m is equal to log base 2 n, where n is the number of inputs and m is the number of select lines. Now, what is the advantage of using mux? The following are the advantages of using mux. It reduces the number of wires in an integrated circuit. Then it reduces the circuit complexity, and eventually that leads to a less cost. And finally, various circuits can be implemented by using only mux, and there exist many different types of mux such as 2 by 1, 4 by 1, 8 by 1, 16 by 1 and 32 by 1. Here in this slide we have shown a block diagram for 2 by 1 mux. So, now let us try to understand the application of mux by considering an example which is 2 by 1 mux. Here n is equal to 2. So, if we use the equation that we discussed in the previous slide, then we will find m is equal to 1. So, the logic symbol for the 2 by 1 mux is given in this particular slide. Here as you can see, there are two inputs I0 and I1 and one select channel which is or select line which is S0. Apart from that, there is another input, that is E. So, here along with S0, E also plays an important role. So, for the mux to work, E must always be 1. Now, if we choose the two inputs E and S0, then we can have the following combination, because we have already said that E must always be equal to 1 to operate the mux. So, if we take E is equal to 0, irrespective of what we are choosing for S, the output will always be 0. Whereas, if we choose E is equal to 1, and if in that case if we choose S is equal to 0, then the output will be based on the input that is coming from I0, and if we choose E is equal to 1 and S is equal to 1, then the output will be based on the input that is coming from I1. So, the final output then can be represented in the following way, that is Y is equal to E inside bracket S0 I0 plus S0 I1, and we can represent this expression in terms of the logic circuit, where we have used one inverter, two AND gate and one OR gate to perform the task for the 2 by 1 mux. Next, we will discuss another example which is a 4 by 1 multiplexer. So, here n is equal to 4. So, we will have to have two select lines, and here the enable option is optional. If we want to use enable, we can use, otherwise we can also neglect the enable option. So, in this slide we have shown the block diagram for the 4 by 1 multiplexer, where we have 4 inputs, that is I0, I1, I2, I3 and two select line, that is S0 and S1. So, the inputs S1 and S0 decide the output from the mux. Here the truth table shows 3 columns, that is S1, S0 and Y. Now, when S1 and S0 both are 0 0, then the output is the corresponding output due to the input line I0. Similarly, when S1 and S0 are 0 1, the output will be due to I1, and when S1 S0 is 1 and 0, then the output will be due to I2, and finally, when S1, S0 are 1 and 1, the output will be due to I3. So, if we represent this output in terms of combinational logic, then we can write it in the following way, that is y is equal to S1 bar S0 bar plus S1 bar S0 plus S1 S0 bar plus S1 S0, and we can represent this expression in terms of the logic gate which is shown in this particular slide. Here we have used 2 inverter and 4 AND gates along with 1 OR gate to create the combinational circuit for 4 by 1 multiplexer. Now, next let us perform a logic function by using multiplexer. So, the logic function that we want to perform can be analyzed by using the following example. Here we have chosen a block diagram for a multiplexer whose truth table we will consider the case where output gives only 1 and rest of the cases we will not consider. And if we choose from the block diagram, then the following condition will give rise to output is equal to 1, and that is when A is equal to 0 and B is equal to 0, that is the select lines are 0 0, then we are getting Y is equal to C, that is the input that is fed by the C input. So, this particular output can be written in the following way, that is Y1 is equal to A bar B bar C. Similarly, the second condition in which we can get output is equal to 1 is A is equal to 0, B is equal to 1, and hence we get Y is equal to C. So, this can be written as Y2 is equal to A bar B C, and the third condition is when A is equal to 1, B is equal to 0, and we get Y is equal to 1. So, in that case we can write Y3 is equal to A B bar. So, to get the combinational logic circuit, we can take the sum of all these 3 factors, that is Y is equal to Y1 plus Y2 plus Y3, and that gives us a simplified form, and which is A bar C plus A B bar, and this is how we can perform the logic function by using the multiplexer. Similarly, we can consider another case by using a multiplexer, and here in this slide we have shown a block diagram, and from this block diagram we can obtain a simplified expression by using the same logic that we used for the previous example. Here from this block diagram we can obtain the output expression as Y is equal to A bar C prime plus A C. So, in this way we can understand very easily how to perform a logic function by using a multiplexer. Next we will discuss about demultiplexer. What is a demultiplexer? It has one input line and multiple output lines, and the select lines decide to which output line the input is to be fed. And so, if we analyze the demultiplexer with the multiplexer, then the demultiplexer is the reverse of multiplexer. So, this is also called as one to many circuit or data distributor. So, if we have m select lines, then the number of output lines can be represented by the following expression, that is m is equal to log base 2 n, where n is the number of select line and m is the number of output line. There is also an enable input, and for the demux to work, E should be equal to 1, and if E is equal to 0, then the demux or demultiplexer will not operate. Now, let us try to understand the application of demultiplexer by using the following example, that is 1 by 2 demultiplexer. Now, here since we have 2 outputs, So, the number of select line has to be 1, and here we can see in this slide we have shown the block diagram for 1 by 2 demultiplexer, where the outputs are 2 in number and the input is 1 in number, and there are two inputs, which is the enable E and the select line S0. So, here because we have discussed that E has to be always 1 for this demultiplexer to work. So, if we choose E is equal to 0, then irrespective of what we are choosing at the select line, our output will always be 0. But if we choose E is equal to 1, then we have two combination, that is E is equal to 1 and S0 is equal to 0. That gives us Y0 is equal to the output that is obtained from I, and Y1 is equal to 0. Similarly, if we take E is equal to 1 and S0 is equal to 1, then we will obtain Y0 is equal to 0 and Y1 is equal to I. So, we can write the output obtained from this demultiplexer in the following way, that is Y0 is equal to E S0 bar into I, and Y1 is equal to E S0 I, and we can write the combinational circuit by representing these expression, and here we have used one inverter and two AND gate to represent the output obtained from the 1 by 2 demultiplexer. Next, consider the 1 by 4 demultiplexer. So, here we will have one input and 4 output lines. Since there are 4 outputs, so the number of select line has to be 2 in number. As you can see in the block diagram, there are 4 output, and including the enable line, there are 2 select lines S1 and S0 and one input, that is I. So, if we observe the truth table, we can show that when E is equal to 0, irrespective of what is happening across S0 and S1, the outputs from the 4 output channels are 0. But when we make E is equal to 1, then we can get 4 combination of S1 and S0, and that is 0 0, 0 1, 1 0 and 1 1, and the corresponding output values are mentioned in the truth table. And from the truth table, we can write the expression of the combinational circuit in the following way, that is Y0 is equal to E S1 bar S0 bar I, Y1 is equal to E S1 bar S0 I, Y2 is equal to E S1 S0 bar I, and Y3 is equal to E S1 S0 I. And using these expression, we can represent the 1 by 4 demultiplexer by the following logic or the combinational logic circuit, where we have used 2 inverter and 4 AND gate to write the final outputs from the 1 by 4 demultiplexer. Finally, let us discuss about encoder and decoder. So, these are combinational circuits which are categorized into medium scale integrated circuits, and these are used to minimize the number of data lines. So, what will be the corresponding number of data lines for a given number of input lines? To find out, let us take the following example. So, let us consider a case where we will collect only those values at the output for which the inputs are high, and in this slide we have shown a block diagram of how a 4 by 2 encoder is fed into a 2 by 4 decoder. Now, since for 4 input lines the inputs are having 2 bits, out of 4 inputs only 2 of them are having high input, and they are I2 and I3. So, we can have maximum 2 output data lines. Now, if we choose I2 input, which is 1 0, then the output will be 1 and 0 at the 2 output data lines. So, if we have n input data lines, then the number of output data lines m will be having the relationship of n is equal to 2 to the power of m. So, the data from the encoder will go to the 2 by 4 decoder and we will obtain decimal value at the output of decoder. So, let us try to understand this particular concept by using the octal to binary decoder, that is 8 to 3 8 by 3 decoder. In octal number, we know that the number of digits which we use are 8 in number starting from 0 to 7. So, for 8 inputs, the number of output will be 3, and the logic circuit can be obtained for the 8 by 3 encoder. Here in this slide we have shown the block diagram for the 8 by 3 encoder, where we have 8 inputs starting from 0 to 7 and 3 output, that is B0, B1 and B2, and the truth table is also shown in this particular slide, where we have 4 columns, that is input B2, B1 and B0, and we have 8 combinations, and the corresponding values are shown in the truth table. So, from the truth table one can easily show that B2 is equal to 1 when we have B2 is equal to 4 plus 5 plus 6 plus 7. Similarly, B1 will be equal to 1 when it is equal to 2 plus 3 plus 6 plus 7, and B0 is equal to 1 when it is equal to 1 plus 3 plus 5 plus 7, and these 3 expressions can be shown by using the following combinational circuit, where we have 3 OR gates in which there are each OR gate will have 4 inputs, and these 4 inputs will give one output, and those outputs are represented by B2, B1 and B0. Now, since we understood the concept of encoder, let us try and discuss little bit about a decoder by considering the following example, that is 3 by 8 decoder. And by using a decoder one can reduce the number of gates. So, let us construct a full adder from a decoder. The truth table for full adder is already known, and we have again shown the truth table for a full adder in this slide, where we have 5 columns, that is 2 input and 1 carry, then 1 sum and the carry output, and we can see that the truth table is same as the truth table we have discussed in the case of full adder. So, the 3 input decoder, the number of output will be 8 by using the equation that we described in the previous slide. So, the combinational circuit for S and C0 needs to be found out. Now, let us denote the input from M0 to M7 in the combinational circuit, and we can find out that the sum S is equal to sum of M1, M2, M4 and M7. Similarly, the carry C0 is equal to sum of M3, M5, M6 and M7. So, these two expressions can be written or can be drawn by using the following combinational circuit, which is attached to a 3 by 8 decoder, and in this way we can obtain a 3 by 8 decoder in a very simple manner. So, viewers, today the discussion was important, and the important points or important take home points that we can give from today's discussion is as follows. We discussed about the half and full adder, which can be helpful for adding numbers. Then we discussed the concept of 2's complement adder and binary adder, how they are helpful in adding binary numbers. Then we discussed the idea of multiplexer and demultiplexer, how they can be useful by considering the example of 2 by 1 and 4 by 1 multiplexer and 1 by 2 and 1 by 4 demultiplexer. And finally, we discussed the concept of encoder and decoder by using the example of 8 by 3 encoder and 3 by 8 decoder. So, viewers, today's lecture is important to understand the integrated circuit that goes into a digital system in a better way, and I hope you would have liked today's discussion. Thank you very much.